Alright, in this video we're going to finish talking about properties of functions. The first things we're going to talk about are even and odd functions. So there's two types of symmetry, and those are going to be even and odd. A function is even if f of negative x is equal to f of x. If we were to look at it on a graph, even functions are symmetric about the y-axis. So things like a parabola that are symmetric about the y-axis are even. And you can kind of see this idea in that symmetry. So if we had, say, a value a and we had some y value b, this negative a is going to have the same, actually be over here, negative a would have the same y value. So if you take the positive and negative x values, plug them in, you're going to get the same y value out. A function is going to be odd if f of negative x equals negative f of x. So if a function is odd, it's going to be symmetric about the origin. So if you think about like a cubic function, it's going to be symmetric about the origin. So if you take that, say, a, and you get b out, if you put negative a in, you're going to get negative b out. So let's look at, actually before we do, one thing I do want to note is while some functions are even or odd, most functions are going to be neither even nor odd. So let's look at a couple of examples. Tell whether the following functions are even, odd, or neither. The best way to do this is to just start with f of negative x. If we start with the f of negative x, that's going to help us with both even and odd. So in this case, we're going to get negative x squared minus 3, right? Instead of an x, we're going to put negative x in its place. Negative x squared is just going to be x squared minus 3. So f of negative x equals x squared minus 3, which is the same thing as f of x. So that's going to be an even function. So if we look at the next one, again, let's start with f of negative x. That's going to be negative x squared minus 2 times negative x minus 2. So negative x squared is going to be x squared. Negative 2 and negative x is going to be positive 2x and then minus 2. So we know right now that it's not even, because it's not the same thing as we started with, because this is a plus 2x. If we think about what negative f of x is going to be, that's going to be negative 1 times what we started with. That's going to give me a negative x squared plus 2x plus 2, and that's not what we got here. So this is neither even nor odd. And let's look at the last one. So f of negative x is going to be negative x to the third over 4 minus negative x squared. Negative x to the third is just negative x to the third, right? Negative x times negative x is positive x squared times negative x is negative x to the third. Over 4 minus negative x quantity squared is just x squared, so 4 minus x squared. So we know it's not even because it's not the same thing we started with. But if we took what we started with and multiplied it by negative 1, we'd get this, so we actually have an odd function. So the next thing that we need to talk about is going to be horizontal asymptotes. Now remember, we've talked about vertical asymptotes, and that's what happens when a function has a factor in the denominator that does not divide out. So that's going to be our vertical asymptotes. But horizontal asymptotes are a little bit different. Horizontal asymptotes, those are going to be a line that a function approaches as x approaches infinity. So as x, actually I'm sorry, plus or minus infinity. So as x goes all the way to the right and all the way to the left, if our graph, our function kind of flattens out to some line, that's going to be a horizontal asymptote. Now, unlike vertical asymptotes, we're allowed to cross horizontal asymptotes. We don't care what goes on in the middle of our graph as far as horizontal asymptotes. We only care about what goes on at the far ends, at x goes to positive infinity and x goes to negative infinity. So there's three scenarios that we're going to deal with horizontal asymptotes, and all of these things deal with rational functions. If the degree of the numerator is greater than the degree of the denominator, then the function will have no horizontal asymptote. So we're not going to have a horizontal asymptote if the degree in the numerator is greater than the degree in the denominator. If the degree in the numerator is less than the degree of the denominator, the function is going to have a horizontal asymptote of y equals 0 every single time. Now, if the degrees in the numerator and denominator are the same, the function is going to have a horizontal asymptote of y equals a over b, where a and b are the leading coefficients of the numerator and denominator. So three situations, all dealing with the degrees of the numerator and the denominator. So let's take a look at a couple of problems and see if we can figure out our horizontal asymptote. So part A, looking at the degree in the numerator, it's 1, right, x to the first. Degree in the denominator is 2, so we have a larger degree in our denominator, so our horizontal asymptote is going to be y equals 0. So if you were to graph this, your function would be approaching the line y equals 0 at the far ends of the graph. So if you want to pause the video for a second, graph this on a calculator and take a look at what's going on, that might not be a bad idea. All right, looking at the second one, degree is 2, degree is 2. So we want to say our horizontal asymptote is the ratio of the leading coefficients. So our leading coefficient in the numerator is 3. Leading coefficient in the denominator is 1. So our horizontal asymptote is y equals 3. So again, if you were to graph it, your function would be approaching the line y equals 3 at the extreme ends. And finally, C, degree is 3, degree is 2, so it's larger in the numerator than it is in the denominator, so we're going to have no horizontal asymptote. And I'm going to abbreviate that HA. So those are horizontal asymptotes. Horizontal asymptotes kind of tell us about this thing called end behavior. So end behavior is just what's going on at the ends of the graph. Now, horizontal asymptotes are a type of end behavior, but it's kind of boring because it just flattens out. So if we're going to look at a function that does not have a horizontal asymptote, that's what we're going to really talk about with end behavior. So to examine the end behavior, what we want to look at is the degree left over when we divide the biggest degrees of our rational expression, and then look at the sign of the leading coefficient. So if the degree is even, again, this is after we divide, and the leading coefficient is positive, our end behavior is going to look like this. So I don't know what's going to go on in the middle, but I know at the ends I'm going to be going up to infinity each time. So how we're going to write that is as x approaches negative infinity, so as we go farther and farther to the left, y is going to approach positive infinity. So going up, so the x values get super negative and the y values get super positive. And we're also going to say as x approaches positive infinity, so as we go farther and farther to the right, as x values go towards infinity, the y values are going to also go to infinity. So if the degree is even and the leading coefficient is negative, the end behavior is going to look like this. So we'll say as x goes to negative infinity, y is also going to go to negative infinity. And as x goes to positive infinity, y is going to go to negative infinity. So you can think of these two things as parabolas, right? We know the shape of a parabola with a positive leading coefficient is going to be like this. Negative leading coefficient of a parabola is going to look like this. So if the degree is odd and the leading coefficient is positive, our end behavior is going to look like that. So x goes to negative infinity, y goes to negative infinity, and then as x goes to positive infinity, y goes to positive infinity. You can think of just a line, right? A line with a positive leading coefficient is going to look like this. and a line's degree is odd, right? X to the first, 1 is odd. If the degree is odd and the leading coefficient is negative, your end behavior is going to look like this. So as x goes towards negative infinity, y is going to go to positive infinity, and then as x goes to infinity, y is going to go to negative infinity. So again, you can think of a line that would have a negative slope there. So let's look at a couple of examples and then call it quits on this video. So describe the end behavior. So if we look, first thing we've got to think about, is this going to have a horizontal asymptote? Well, our degree is bigger in the numerator, smaller in the denominator. So this doesn't have a horizontal asymptote. So we've got to think about those four rules we just had. If we think about x to the third divided by x squared, that's going to be x to the first. So that's an odd degree. Your leading coefficient is 3. So that's even leading coefficient. So even leading coefficient, odd degree, looks like that. So we'll say x goes to negative infinity, y goes to negative infinity. As x goes to positive infinity, y also goes to positive infinity. On the second one, we have a 4 and a 2, so 4 is bigger than 2. We don't have a horizontal asymptote. If we think about x to the fourth divided by x squared, we're going to get x squared, even degree. If we look, we have a negative 3. So even degree, negative leading coefficient, and behavior is going to look like that. So as x goes to negative infinity, y goes to negative infinity. As x goes to positive infinity, y goes to negative infinity. So that's going to do it for this video. We'll see you in the next one.